What I want to talk about is an approach that we've been following at the San Diego Supercomputer Center to actually build preservation environments and apply them on large scales, at scales that a national archives would be able to use, but at the same time have an approach that would enable a small state archive or a small group to actually use the same technology. So when I talk about building a preservation environment, this is going to be what are the software components, what are the mechanisms we use that allow us to actually implement such an environment and use it for very large-scale collections. One of the things we've noticed is that the technology we're providing is actually used by a wide variety of data management environments. We aren't restricted to support for just a preservation environment. I use the word persistent archive here, which I will need to explain, but also for building shared collections that are distributed geographically across multiple sites, or for building digital libraries. We wanted to coin a term that would describe the infrastructure that could manage technology evolution. When we have been storing data at the San Diego Supercomputer Center, we noticed that every 3 years we would migrate to a new type of archival storage system. And in the process, the transformation from the old technology to the new technology would be onerous. We'd take the system down for a week while we're migrated the metadata catalog. We'd have to copy files from one tape media to another. And since we did that transformation 6 times over 20 years, the supposition was there's got to be an easier way. So the persistent archive is the technology that allows the preservation environment itself to evolve over time, incorporate new technology, and minimize the effort required to migrate from the old technology to the new technology. The concept behind it is this building a shared collection. We associate all of the properties required to manage the data with the shared collection itself, independently of the choice of storage system. So we'll go into that and look at multiple examples of groups that are managing data across a wide variety of types of storage systems. So the 3 terms I've discussed, data grids, digital libraries, and persistent archives, actually are just different sets of management policies for organizing, maintaining your particular set of data. So in data grids, projects want to share data across multiple sites, and they focus on the access. In digital libraries, they focus on the services that will be applied on top of the collection. And in the persistent archives or preservation environment, the challenge is managing authenticity and integrity of the records while the underlying technology evolves. This is an eye chart, which I'll interpret for you, but the goal of this is to show that the technology scales. These are collections that are currently being managed at the San Diego Supercomputer Center using the storage resource broker technology. In aggregate, there's over 650 terabytes of data in these collections, over 100 million files, but an individual collection may be as small, in this case, as 100 gigabytes. It might be as small as only, let's see, 200,000 files. The largest collections here range up to 200 terabytes in size, with collections that have over 50 million files in them. So the technology is scaling from very small collections to very large collections. One of the characteristics that we observe is that the number of people who are involved in building, maintaining, curating, preserving that collection varies typically from around 50 people to 200 people for each of these collaborations. So this column on the right is the number of people who have permission to come in and do the curation, do the addition of additional material to the environment. Another characteristic is that the effort that's going into this is exponentially growing. In 2002, there was roughly 28 terabytes of data in this environment, 200 terabytes in 2004, and now there's over 600 terabytes. So it's growing at more than a factor of 2 in size per year, and the number of communities that are involved in doing this is also growing substantially each year. So the ability to manage shared collections, to put together both preservation environments and digital libraries is of great interest to many communities. For the particular area of persistent archives, the ones on this slide are collaborations with the National Archives for the US, a National Science Digital Library which preserves web crawls, a UCSD Libraries image archive, and then a persistent archives testbed which works with state archives within the US for preserving their particular collections. So the groups using this technology span a wide variety of communities. We claim that a single type of data management infrastructure is capable of supporting all of those environments. And part of the proof is the fact that we're applying this technology for all those environments. The technology is called data grid technology. It's part of the technologies that are coming out of the Global Grid Forum. This is an international standards group which is trying to understand how to manage computation and data across distributed resources. The particular implementation we deal with is the Storage Resource Broker, which has been developed at the San Diego Supercomputer Center. So the Storage Resource Broker, or SRB or SERB, is the software we install to manage distributed data. The way you would use this environment is you can register the existence of a digital entity, a file, a URL, a query command, whichever, into this environment, assign ownership, who's allowed to add metadata, who's allowed to create new items within a collection, assign descriptive provenance metadata. One of the challenges of this environment is allowing each group to specify their own choice for descriptive metadata and for the organization of that metadata. So this environment had to support extensible schema, where you can build a logical representation of the structure that will be used for your metadata, and then map from that logical representation to the actual tables that you use in your own database or in tables that are put into our metadata catalog for the SERB. So this is quite sophisticated environment that is extensible, allows you to update, change, and manage the data as needed. One of our major constraints was the fact that modern storage systems do not provide the support for state information that distributed collections require. So when we work with multiple communities, they want information like audit trails or versions or checksums or backup copies or replicas, where the replica is stored, etc., as information they associate with each record in this environment. And a modern file system like Unix or Windows isn't aware of the existence of these types of state information, so we have to manage them independently of the storage system. We actually chose to manage all the state information you normally associate with the file, such as its size, its owner, when was it created, and can manage those attributes independently of where the data is actually stored. A second challenge was this system had to be able to support data that was in a wide variety of storage environments. It might be on a Windows file system, it might be out in a Unix file system, in an archive that uses tape, in a blob or binary large object in a database. All of those objects should be accessible through the same access mechanisms. Our final challenge was that users have a wide variety of preferred access mechanisms. Some want to use DSpace digital library technology. Some want to use Java as a standard interface for talking to the storage. Some groups come in with the Open Archives Initiative protocol for metadata harvesting, etc. So in this case, we have on the order of 20 different access mechanisms that a community can use to get to the data in the distributed environment. The way this works is each location where data is going to be stored has a software server installed, And then from the client, from the application that's trying to get to this data, we talk to a local SERB server. It's a peer-to-peer arrangement, so this SERB server can talk to the one that understands where the metadata is located, access the metadata that describes each object in this environment, look at that metadata to determine the actual physical location of the data, go to that site where the data is actually located, retrieve it, and send it back to the application. This works very well for small files, files that are up to 1 megabyte in size. For large files, the desire is to use parallel I/O to move the data from the site where it resides to the requesting application. So part of the challenge of this environment was guaranteeing that we could support parallel I/O from the location where the data actually resides back to the requesting application, and that way be able to scale up to these collections that are hundreds of terabytes in size. For us to move 1 terabyte a day means we need a bandwidth of 11 megabytes per second. So this requires relatively high-speed networking support. When we built this system, we then looked for collaborations with many communities to verify that this really was generic software capable of supporting not only preservation environments but also digital libraries. So there is an interface between the DSpace digital library developed at MIT with such that it can store data and manage data that's in a distributed storage resource broker data grid. There's also an interface from the Fedora digital library so that it can access data within the distributed data grid. Then these two particular digital libraries provide their own set of services on top of the distributed data. We have built a variety of preservation environments using this technology. The largest is the first one listed here for the National Archives research. It's actually a research prototype persistent archive. There is a production system that the National Archives is building under contract with Lockheed Martin, and the research prototype is the environment that defined the concepts under which the ERA, the Electronic Records Archive, will be built and will follow. So the National Archives, and I'll have a slide about this later, is managing 2 terabytes of data in this environment at the moment. The technology is used for the California Digital Library, Digital Preservation Repository. We use it to support the National Science Digital Library, and again, I'll have a slide on that. The NSDL has a central repository where they register URLs pointing to educational material. The challenge is that all of the material is posted on the web. When we first crawled these websites, we had an error rate of about 1.5%. Now when we crawl the websites, we get an error rate on the order of 25%, predominantly because the projects that funded the creation of the material had a 2-year lifetime, and we're now 6 years into the project.
So error rate being defined how?
We try to crawl an item which was registered, and it's either file not found, site not accessible, or 10 or 12 different possible error messages. And so therefore there really had to be a preservation environment behind the material that had been, whose creation had been funded by the federal government. So currently there's 750,000 URLs registered into this environment. It's about 13 million web pages. It's about 3 terabytes of data. If you reference an item that is registered into the NSDL central repository and it's not there, you can click on a button and retrieve the item directly from the data grid, from the preservation environment at SDSC. We throw on a little header at the top showing that this is the archived version. You aren't looking at, it's not the real version, it's the archived version. But all of the links were reset, so we replay the web page out of the archive instead of the original website. Another example of a group that is building a large collections is the Southern California Earthquake Center. This is a group that provides their own services for interacting with their particular data. So they display seismograms. They allow you to do them side by side. They give you descriptions of the structure of the faults that drive the seismograms, etc. So their services are highly tuned to their particular application. but they're managing massive amounts of data. One simulation that was generated here had over 47 terabytes of data generated, several million files. So large scientific collections need digital library support, and because they want to keep this collection around for 10 years as a reference digital data set, they need to worry about preservation, about moving this collection onto new technology over time. Another group is Real-Time Observatories and Applications Data Network, RoadNet, where they're taking data from sensors in the field in real time, bringing them in to a collection that they then manage, and they want to be able to access this observational data for long periods of time. So they're very worried about how do they preserve this type of data and make certain it will remain accessible, especially when they have multiple groups independently collecting the data. The Banera Persistent Archive is a version of a preservation environment that uses 3 independent data management systems. There's a data grid sitting at the National Archives based on what we call a grid brick, commodity-based PC-type disk, with a database for managing all the state information, all the provenance metadata based on Oracle. At University of Maryland, there's a second independent data grid. In their case, they use the Informix database, and they have a different commercial provider for their disk technology, plus they have an archival tape system. In San Diego, we have a third independent data management environment where we have an Oracle database, a different set of commodity disk, and a different type of archival tape system. And the goal is to show that if we build a set of records with the appropriate authenticity and integrity metadata that's housed at NERA, we can replicate that collection into both of the other data grids, that we can go through and validate that both the metadata and the data have actually been replicated and are consistent across the multiple environments, that we can federate the data grids so the National Archives can actually, through their data grid, store data on resources at San Diego. So we've been working with a variety of implementations of types of federation between these grids to investigate which one best meets their preservation requirements. Groups do this on an international scale. We aren't located to just offices or institutions within a given continent. So this is the Worldwide University Network Data Grid. Participants are here mainly in the UK, but it involves sites in Europe and the US. And the goal is a data grid that spans all those sites to promote research and collaboration in a variety of disciplines, whether it's in biology, distributed data management, or data analysis, medieval manuscripts, etc. And in one of the collaborations, there's a biology grid where collaborators between California and the UK are jointly developing new biomolecular model simulations. And this group builds its own data grid, but it will federate with the Worldwide Universities Network Data Grid. There are groups that do this with data grids that span the world. So the Keck High Energy Physics Data Grid has sites in the Far East, in the Europe, and the US, and they can move data all the way around the world from one data grid to the next within this environment.
Define the data grid.
The data grid is the set of software which manages the distributed resources. Here's a high energy physics group in the US called BABAR at the Stanford Linear Accelerator. They have moved now over 170 terabytes of data to Lyon, France, and they're planning to move data at the rate of 5 terabytes per day this year for the BABAR experiment from Stanford to Lyon. And this is a major production facility. And there are groups doing this for astronomy. This is the National Optical Astronomy Observatory, has images being taken on telescopes in Chile, and those images are being moved to the US for preservation and analysis. So they're at the point now where this is their production facility to migrate, or at least be able to get all of the data from Chile to the institutions in the US that want to process the data. The technology has a very wide variety of applications across many different countries. Taiwan, the UK, Australia are major users of the technology. The Sarah group in the Netherlands is now going to be working with this data grid technology. So there are a wide number of institutions that want to build upon the ability to manage a shared collection that's distributed across a large number of resources. So what I'd like to do is to go into some of the concepts behind how you make this work and why those concepts are important to preservation environments. When we built this environment, there were actually 3 or 5 main layers. There's the layer at the bottom, which manages access to the storage system. There's the layers in the middle, which maintain consistent information, which manage access, authentication, and authorization. There's the layer that manages federation between independent data grids. So if I have established a data management environment in San Diego, the servers I talk to are able to communicate to servers in another data grid, say here in the UK. And then there's the highest level, which is the set of application interfaces that you can use to gain access to the distributed data. So there are a wide number of implications of this architecture. One is that we can add a new access mechanism at will, and many groups do that. And what happens then is as soon as we provide a new access mechanism to this environment, through that client, you can gain access to data that's in any of the storage systems. So some people use this environment strictly so a modern access mechanism can talk to their legacy storage system, which knows nothing about that access protocol.
Now you have only, your databases here are all relational. Is there any reason for that?
We use relational databases to actually manage our state information. And the reason we do that is because we're trying to do queries across millions of files, millions of records. We've experimented with XML databases, and they scale to 55,000 objects. So it's a little bit small.
You don't like object databases?
We have built interfaces to object-oriented databases, but the challenge is managing extensible metadata without having to revise a class structure. So in our case, we can add arbitrary sets of metadata to an individual object within this environment. We can build a collection, sub-collection hierarchy all the way down to the single item level and dynamically add that metadata at any point in time.
And relational database is well suited to that?
Our interface that sits on top of the relational database is well suited to that. The typical database that you normally think of has a fixed schema. There are tables you predefine, attributes you predefine. We aren't in that world. We're in the world where we're managing the catalog that happens to sit in the relational database. And the capabilities we have to provide on top of that relational database are the schema extension, the ability to add new attributes, the ability to add new tables dynamically, the ability to do bulk metadata load into the database in parallel, so we can have multiple streams pushing metadata into the system, the ability to import and export metadata out of the catalog using XML. So we had the ability to import XML running on Oracle before Oracle published that as a capability. So there are a variety of things you want to be able to do to manage the catalog that holds the state information. We choose to use relational databases because currently they scale best for large numbers of records. When we talk through this standard repository abstraction, we're actually providing a standard set of operations for interacting with each of the storage systems. So these standard operations are typically ones like being able to read data or write data or list what files are present at the system. But it ends up being a much more extensive set. I'll get into that in a moment. The objective of this environment is to have a sufficient capability that we can automate all aspects of data management, whether it's storing the metadata, whether it's managing queries across the collection, whether it's retrieving the file from some remote location where you don't know where it is, but the data grid does, and have all of that be able to be automatically executed directly from your application. So this is hands-off environment where the application can do all the work. At the same time, we have interactive interfaces, so you could go in and do each command separately and interactively. manage this environment. This has been developed by a team now of 15 people at the San Diego Supercomputer Center over the last 8 years, basically since 1996, 1998. It's about 300,000 lines of C, so it's not a large code. Large codes are millions of lines of C. It's been funded by a very large number of projects, so the requirements behind the capabilities that are provided in this environment were the requirements that came from the groups that were actually using the technology. And the groups using this ranged across multiple federal agencies, across both groups that were using preservation environments, digital libraries, shared collections. This original project funded the design and development. After that, everything was an application until we got down to this project, which finally funded a new generation of technology. So this technology continues to evolve, but it's been evolving under pressure from the user communities to provide their particular data management requirements. The current release is version 3.4. Typically, there's been a major release practically every year. When I talked about the ability to apply an arbitrary access mechanism and get to data in somebody else's storage system, we did this by differentiating between the capabilities required by the access mechanisms and the capabilities that the storage system provided to the outside world, the protocol the storage system used for communication. An example will be if I'm storing data into a tape archive, typically the only operation I'm allowed to execute is to either get the entire file or store an entire file. But we wanted to support partial file read and write. So our interface, when it talks to an archive, has to grab the file out of the archive, put it on disk somewhere, do the partial read and write on disk, and then when we're finished, put the data back in the archive. So what we do to interact with the storage system is a standard set of operations where we've figured out exactly what we need to do in order for those operations to work on that legacy storage system. Similarly, at the top level, when the access mechanisms comes in, there's a standard set of roughly 100 operations that access mechanism might do related to manipulating metadata, manipulating data, assigning access controls, replicating, moving the data around. And we have to map from the mechanisms that particular client is expecting to use to the rest of the storage systems. So we have two levels of indirection, one for the clients and one for the storage. This means that if we add a new storage system, all of the prior clients can now access it. If I add a new access mechanism, it'll work on all the previous storage systems. They're completely decoupled. When I talked about the type of operations that were done at the remote storage system, we started with simple read and write. But since we're working in a distributed environment where we've replicated data at multiple sites for disaster recovery or availability, it turned out there were a variety of other operations that had to be done in order to keep the system interactive. So when we read and write on a file, then everybody started requesting a different set of capabilities like audit trails, who are the people actually doing the read and writes. Version numbers, when I write a new version out, can I annotate it with the version number? Supporting checksums so I can verify that the file was actually moved correctly and wasn't corrupted by the transport. Synchronizing replicas, so if I change one replica, all the other replicas can be synchronized so they also have the changes. Latency management is the challenge that when we work with wide area networks, we can't afford to send small files one at a time across the network. We worked with the Michigan Digital Library and they tried to load 70,000 small files one at a time into a digital library in San Diego. And they rapidly discovered that the overhead of interaction for each file was so high, it just was not feasible. It was going to take them a week, 2 weeks in order to do this. So we have to provide, or had to provide mechanisms to aggregate small files. So I take 1,000 small files, I pack them together into one large file, send the one large file over the network, simultaneously load all of the associated metadata, the owner, the creation date, etc., for that file in parallel into the metadata catalog. And then we can get performance in the aggregate that's much higher than the performance you would get for an individual file. We also had the problem of dealing with large files. If we have a very large file, 2 gigabytes at a remote site, and we want to extract a cutout, we can't afford to bring the entire 2 gigabyte file across the network and then at the client do the small cutout and return 5 kilobytes. We have to be able to do that procedure directly at the remote storage system. So part of this is being able to apply filtering and parsing of data at the site where the data actually resides. Examples of this include metadata extraction, so I can mine metadata out of a remote file and then load that metadata in bulk into the metadata catalog. So I've already talked about the metadata management, the types of operations we had to provide on catalogs that sit within databases. This environment is extensible, another major requirement for preservation, because I know in the future there will be additional capabilities that will be required. So in this case, we've been adding over time a wide variety of different types of storage repositories and a wide variety of different types of database into which we can put our metadata catalog. The next one that will be on the list will be SQL Server, because that's a high request. But our dominant database, or the highest performing database we interact with right now, is Oracle. You can put metadata into a Postgres catalog, MySQL, DB2, Informix, Sybase, etc. When we worked with this environment, we thought that if we provided a standard set of mechanisms for interacting with this environment, everybody would be happy. And based on our experience, those 3 access mechanisms were C library calls, so an application could directly access this environment, shell commands, so you could interactively sit at a terminal and access this environment, and then a Java interface for web browsers and portlets. It turns out that on top of those 3 interfaces, we've had a continuing sequence of requests for additional ways to access the data in the distributed environment. And so they range from the web services description language for services-oriented architecture interactions to groups that build workflow environments that sit on top of this environment to groups that are porting digital libraries like DSpace and Fedora sitting on top of this environment. So we keep adding new interfaces that will, every time we add the new interface, you're immediately able to access all the data that's already in this environment. So I've got, plenty of time. I get to talk about what I view as the major challenge for preservation. When I think of the preservation of hard copy pieces of paper, what happens is the person who wrote the paper hands it to the archivist, who annotates a catalog saying this paper was received by this institution with this set of provenance metadata, etc., and marks that up in their catalog, and then puts the piece of paper in a cardboard box and puts the box on a shelf. So they've extracted the paper record from its original creation environment, the author, and put it into their preservation environment. And it was very simple. It was a physical operation. We have to do exactly the same thing for digital records. We have to extract them from the environment in which they were created and put them into our preservation environment that the archivist will manage independently of the original person. Our challenge is that when somebody creates a digital item, a Microsoft Word document, an image, or whatever, it has many properties which are actually associated with the storage system that they're using. So the location where they created the data is an IP address. It's on some computer. The name that's given the file in their environment depends upon how they set up their file system naming convention. Typically, the path name changes. The name that they have, the identity under which they created the file, their username is unique to that system. The context, the metadata that storage system saves for the file, creation date, size, owner, etc., is unique to that system. And the access constraints, who's allowed to actually manipulate the file, change it, write it, etc., is unique to that environment. When we work with a preservation environment, we have to provide a namespace that the archivist controls for each of those naming criteria. And the reason is that when the archivist gets this digital record and puts it onto a storage system, the physical names at the storage system are now local to whatever version they picked. And when they migrate it to a new physical storage system, those names may change in time. So how do you track authenticity of a record where its name changes, depending upon when you were working with it? So we wanted a set of naming conventions that were invariant. These naming conventions for the users, the file names, the context, the metadata, provenance metadata we're managing for the file, do not change as we move the file from one storage environment to the next. They're under the control of the archivist, they're invariant, and they can be global across all the storage systems that participate in this data grid. The nice one is that our controls, access controls we make in this environment are now relationships between a username that the archivist is managing and a file name that the archivist is managing. So the permissions for who's allowed to manipulate that file, add descriptive metadata, is under the archivist control. And as you move the file to the next environment, the same controls apply. They do not change. They're no longer subject to the requirements of the storage system. We go one more level of indirection because it's not only the fact that we have to map from the logical names the data grid is managing to the actual storage locations of the physical storage device, but we can do this mapping between data grids. So if we build a preservation environment at the National Archives, they're controlling all of their namespaces independently of the rest of the world. They can map their names to the namespaces used in San Diego for the second data grid, and they can decide which of these namespaces will be mapped from one site to the other, what are going to be the access controls that are shared between the data grids. Will data grid A be allowed to write on resources in data grid B? Will a user who has an identity in data grid A be known by data grid B so they can apply access controls on it? Or will the user in data grid A only be able to access public data in data grid B? So you can build a quite wide variety of federation environments, and many of them are running here in the UK and the UK eScience data grid for controlling how you want to share data from one shared collection to another shared collection. One reason we're interested in doing this is because there are a very wide variety of ways that you can lose data. And the preservation environment can't afford to lose all the data that it's organized. So we might have media failure. I wrote the data to tape, and then the tape was dropped on the floor, and I can't read the data anymore. We see problems with vendor systemic errors. I wrote the data with a tape drive, and the tape drive had bad microcode in it, delivered from the vendor as bad microcode. And so we have to learn when that happens and figure out how to upgrade the system. So there are vendor-specific errors. We have problems with operational errors. Anytime we change to new hardware, the old procedures may not work exactly the same, and if the operators try to run them, they're at risk that they will overwrite data on tape. So we have to always worry that whenever you're managing an environment which is evolving, the procedures themselves have to evolve, and how do you keep them synchronized? We have to worry about natural disasters. We have to worry about malicious users. We have people pounding on the system daily to see if they can get in. And we would like our preservation environment to provide the minimal number of copies at least to mitigate against all those possible sources of risk. So we would like 3 copies. The first copy supports the interactive access. The second copy is run at a remote site by a different administrative domain using different hardware. So suddenly I've covered 3 of the risks. Because it's a second copy, I've also covered the problem of media corruption. I have 2 copies. If one is bad, I can go to the other one. I need a third copy, which is in a deep archive, which is protected from malicious users. So this is the copy that has no public access. It's only accessible by the preservation community. But nevertheless, there's a way to do bulk loading of data over networks into this environment. So this seems to be a non sequitur. How do I have something connected over a network with no network access? And the answer is we have to build a very particular federation of the 3 independent data grids. So I have the environment in the external world, which is managing the data that's sitting on multiple storage systems. But I have 2 other independent data grids. I have the deep archive, and the goal is that this archive should not have any presence that can be seen by the outside world. Anybody in this environment should not be able to identify a person or identify a location associated with this deep archive. So between the external world and the deep archive, we put a staging grid. One of the things we're able to do with this environment is work through firewalls. So if an archivist in this zone registers their identity into the external world, they can then pull data from the external world through the firewall onto the staging zone. We do the same thing then. An archivist from the deep archive registers their name into the staging zone so they can pull data from the staging zone into the deep archive. What happens then is the only thing that's known to the external world is the name of the person who is running in the staging grid zone and its location. Nothing is known in the external world about the deep archive. So you can build a system which has a logical air gap. It's as if there was an air gap between the environments, but by the appropriate use of firewalls, you can put another firewall here and a private virtual network and guarantee that this zone can only talk to, this data grid can only talk to that data grid. And you can only pull the data in under commands issued from within the archive. You've now isolated this environment from the external world. You can actually push data the other way. This archivist could push data into the staging zone, and then from the staging zone, the second archivist could push data to the outside world. So you can build the environments that are required for long-term preservation, for mitigating risk of data loss, for building the global persistent namespaces required to identify all the records in the environment, and for managing the authenticity and integrity metadata. And I welcome any questions.
This level of security is very missile silo-ish. And the question is how long it can be made. Just as the security precautions on our missiles and nuclear weapons are, how long they can be maintained, the same questions apply here. This has to be funded for a very long time.
There's a major question in all of these environments for the sustainability and governance. And what are the appropriate models to guarantee that we will continue to maintain the records that we've assembled? The favorite example is Library of Alexandria was going to accumulate all the world's knowledge, and then they burned it up in one fire. So we want an environment where if one component is destroyed or its sustainability goes away, we still have a copy in another environment which hopefully is being controlled under a different sustainability model. So I would like the environment where if this group has funding from the federal government, this group has funding from an institution like a university, and there could even be a commercial version. So there are multiple sustainability models that get federated to guarantee no matter what happens to one model, the others hopefully will still preserve the data.
That was sort of going to be my question as well, because I can understand the technology. It's very, very impressive, but it's sort of, there's no problem that can't be solved by adding an extra level of indirection, so I understand that. But sort of the management, the social and the political aspects, sort of who owns this, then who owns the archives, what happens if the owners of the archive, that organisation goes out of business and all, who's the overall sort of guiding light?
When we built this environment, what we observed is that the communities who are interested in the data are the communities that collaborate, I'll just stop there, that collaborate on the creation of this environment. So in the astronomy community, they all want access to the images taken by telescopes, and they collaboratively build the digital library that gives them the standard access mechanisms, the standard naming conventions. And then it's the community, which is spread across multiple institutions, which pushes and comes up with ways to guarantee they'll be able to continue access. From the perspective of a university can differentiate itself from other universities by demonstrating expertise in a given area of science or arts and humanities. And part of that expertise is having the ability to access the digital reference sets, i.e. the images or the documents that that community bases its research upon. So we think there's a very strong incentive from universities to build their digital reference sets that promote research within their particular institution. But there's not only at the institution level, there are collaborations across institutions now where people recognize that if they share the data, both sides can gain a benefit, gain access to the newest data that's becoming available. And then when we work with the National Archives, they are operating under federal mandates for preserving the records, and therefore they will be around as long as the federal government's around.
I was interested in the archiving of documents that were sort of linked to internet records. So you mentioned that if some document was archived and then had a link to another document, you changed the link so it linked into the archived version of the other document and so on.
Yes.
How do you deal with the problem that some of these documents are dynamic and that these links are created at view time in the browsers and using technologies like that, and you've got dynamic websites where the actual page that you see in your browser has been created for you once only and never again?
There are several approaches. The ones I'm interested in is for the content that's being dynamically accessed, there's a database behind that environment which are querying to generate the web page. And what we should really archive in that instance is the database itself, and then provide the service on top of that database which allows the similar type of access, how you query that database to extract data out and present it. When we work with the scientific communities, they use that approach. So their database is the image catalog, which has recorded within it the location of every star and galaxy in the sky. And they have built a standard sky query interface to allow you to apply operations across all of those recorded records and then plot each location on top of an image so you can correlate how good you extracted the objects from the images, etc. So the community is actually working at building those interfaces today. And when we choose an environment to preserve, we want to choose the digital reference sets and the services that the community wants and needs, and then preserve those. So we try to solve the problem by looking for either the database and the service that is able to interact with the database, but one which is representative of the community.
Yeah, I guess that's the key. I mean, if you store the database, then in principle you've got everything. But often, and I'm perhaps thinking in terms of commercial websites and so on, there's that middle layer that presents the data.
Exactly.
And the presentation is A, of interest in itself, but B, is non-trivial. But C is running on some bespoke software that they might be reticent to give you and all that sort of stuff. And it might, in the case of one company I worked for, they didn't know how it worked anyway.
So companies can put insurmountable obstacles in face of preservation.
Yeah, exactly.
And
is that of interest? Is that problem of interest to you to sort of get around this in any way? Or are you just going to say, well, if you give us your database and you help us understand how it's presented, we'll work with you? But
we prefer the latter approach. We have gone to databases and crawled them an item at a time, extracted all the information content out of the database, and rebuild another database. That's very laborious. It's much easier to just grab an entire database.
And they can also keep you from doing it. Right?
Yeah.
Yes. So you aren't guaranteed that you'll be able to preserve in something that the group that built it says you can't preserve it. Yes.
This is actually reflecting a statement back to you that you made at the all hands. When you've got a database, how do you know it's not corrupt in any way?
One of the databases we worked with was the Life Cycle Data Requirements Guide for the National Archives, This is a set of hierarchical provenance metadata that they associate. So there's a record group and its metadata, a record series. The record group is the federal agency. The record series is a particular set of documents that are being submitted. Then there's the file folder, the place that aggregates together all of the elements associated with an item, and then there's the actual object. And so at each level there are multiple sets of metadata. Some of the metadata is cross-linked. So down at the item level, I also record which group it belongs to, and at the group level, I record that group. So you would like to put consistency constraints on the descriptive preservation metadata so you can go in and validate that those consistency constraints are actually honored. And we did that for all of the records that were put into their electronic access project, where they took roughly 250,000 images and put them online. And we were able to show that by looking at the metadata attributes for each item, we could correctly identify which metadata attribute should be present across the entire collection, identify classes of anomalies where there actually were problems with what was associated with each record, and then also do this analysis where we compare that the group numbers matched, etc. From the regular expressions we created, dynamically derive the database tables, and then populate those database tables with the metadata and support queries against it. So effectively, we took the metadata as presented and dynamically reinvented the database and supported queries on the combined environment. So you can put consistency checks on your preservation metadata.
So how big does the data sample need to get with present technology error rates before you get into a problem with just your 3? Because you've got to have 2, presumably, which are right when 1 is wrong.
So our challenge is that what are the consistency checks we can do to correct as many of the errors we see as possible? So if we move data, we can't rely on current transport protocols to move the data correctly for large sizes. So if you try to move more than 8 terabytes, your data will have some errors. And therefore, you have to independently put a signature on the data that can be evaluated after it's moved to verify that it made it there correctly. When I store the data in the storage system, it could be corrupted at any time in the future. A cosmic ray could come through and flip a bit on disk or on tape or wherever. So periodically I have to read the data off the tape, validate its checksum. Is it still good? If it's not good, then I have to throw it away and go to one of the copies that's still good and replace it.
My question is, if that happened every day, then you would never be able to catch up. So how close are we to that?
Oh, I see. So it depends upon the type of storage system. We have a commodity disk that we check every weekend. So the disk itself goes out and validates the checksums and proves that, yes, the data is still good. And our error rate is that we will have a failure on that disk once every 30 days. So we want to check at a rate about 4 times the expected failure rate. If we write data to tape, then it's longer. Once we verify the data made it out there correctly, it's a longer period of time before we have to go back and recheck. And we hope that that time period is sufficiently long, like 3 years, that by the time we need to do a check, it's time to migrate to new technology anyway.
You talked about scalability in terms of number of records and numbers of files. With the technology model, have you done any tests for scalability of number of independent data sources connecting to an MCAN?
We've gone up to 87.
Right.
We are interested in seeing how large that number can scale. It's a table in a database.
Yep.
And so it really will depend upon how we optimize the database for interacting with that table. But databases are supposed to go to 1 billion records nowadays. So when we register information about each server, they're all independent. Each is a peer-to-peer environment, and therefore it really is a small number of tables that you're actually managing. Yes?
Taking that scalability question a step further, one of the things when you talk about these institutions here, they're quite large. You said you were working with states and smaller organizations. how would a small archives actually be able to utilize this technology, which seems to be designed for larger institutions, but yet will be required for smaller institutions?
One way they do it is by seeking collaborations. So when we built this persistent archives testbed for Kentucky, Ohio, Michigan, and Minnesota archives, we managed the metadata catalog in San Diego for them. So the only thing that was sitting at their site was a commodity disk called a grid brick and a SERB server, which we helped install. What they actually did then is they weren't managing the technology, they were managing the process of accessioning data, appraising, arranging, describing, etc., the records that were being brought into the environment. And we managed the metadata catalog for them independently. We had our own database administrator helping them. Now they're at the point where they're starting to say, we know how to run databases. We could run a database locally so the database doesn't have to be on the other side of the continent in San Diego. And they're getting to the point where they will now run the entire environment locally. They like this approach because it allowed them to share risk across 4 states. One state isn't off on its own trying out new technology. They're doing it in collaboration. They feel safer. The other one is that they did not have to have all of the expertise in-house. They were jointly developing technology, so there are multiple groups you can go to get support for how you make something happen. So we have SERB chat, and people respond on SERB chat to requests that are posted from other institutions. There's a community developing of what's a good way to respond. So you want the shared risk, the shared expertise, the shared management initially, and then eventually most groups want to bring it in-house so that they can control what's happening.
For example, with our AI, to the IRC MCAT. So you'd run a service over here and connect into our MCAT, and the longer term thing there is then to connect that into the other IAs.
What is an MCAT?
It's the metadata catalog that manages all of this state information or metadata attributes. So we got to put it somewhere. Yes.
Oh, no, go ahead. It's okay. Grid networks give us this wonderful capacity for dynamic linking and interoperability across heterogeneous collections. And some of the work that's being done in the DLOS Network of Excellence in Europe is both working on preservation strategies, but also ontology-driven interoperability. And I wondered whether or not you'd comment about the kind of strategy you would see as the best strategy for linking these two very important areas of research.
We're collaborating with the Fedora group, which is providing the ability to impose ontologies on top of the descriptive metadata. So in their case, they can use RDF and associate relationships between items, build hierarchies, support queries based upon those links. And that way you can decouple the ontology from the underlying data management. So for the Fedora community then, there is an interface from the Fedora services into data that's being managed in the distributed environment by the data grid. Within the data grid itself, though, we want a similar capability. We want to be able to characterize the management policies independently of how the data grid chooses to actually implement them. So we need policies for how frequently do we check the checksums, what's the correct number of copies to have, where should the copies be located, when should we make certain everything's been synchronized. So there are a lot of management policies you get to impose. We are starting a collaborative development project to be able to apply these management policies, rules, consistency constraints directly within the data management environment. So we see multiple levels of rules, relationships, consistency constraints that are required. At one level, it's the set of rules and policies required for governance and stability and sustainability. At another level, it's the relationships that are required for imposing an ontology on top of the descriptive metadata, for being able to search within it and manipulate it gracefully. And at the bottom level, it's all of the rules for actually how you manage the placement and movement and replication of the data. So ontologies in the future either helping express management policies or these consistency rules become extremely important, because that's how you actually manage and control the environment.
Well, I'm glad to hear that, since we're already working with Carl
Yes.
Gozzi on Fedora. But I wondered if you would comment whether or not there's a closer relationship between creation of data, so going down even another level, as it were, and preservation. So creation of data and preservation have to be more closely allied, rather than just focusing on the management of data.
Correct. So as you try to come up with ways to correctly assign the provenance metadata, you need to be involved in the creation process. The only saving function that we've observed is that when groups build very large collections, most of the cases those collections are homogeneous. So they use the same approach for every item. So all the images taken by the astronomy community are in a FITS format with a standard header I can extract metadata out of. It's very hard to build a large collection of inhomogeneous data, because then every item is unique and it's a separate interaction. So as these collections grow in size, or the collections that a given community is creating, there usually is some sort of standard that that community is using to help automate the creation of the data. And therefore, part of our creation process is understanding those standards the community has self-assembled to help them create the data which is now going to be preserved. But it requires interacting with each community, because they all have slightly different purposes, slightly different ways they have to organize the data and manage it. But that's the way out I see in the future. I have to define the community I'm working with, understand the standards that that community is now self-enforcing, and then preserve that.
Look at something like the way BitTorrent tears everything into small fragments and yet maintains its structure. In principle, you could shred this whole thing up and BitTorrent it around to many locations.
Yes?
And just thinking ahead.
So there are multiple preservation environments. So there's locks, lots of copies keep stuff safe. There's BitTorrent. There's various Ocean Store implemented by UC Berkeley.
Variants?
Different versions of
Ocean
preservation
Store.
environments, such as Ocean Store. And so these environments all focus on some aspect of trying to manage the data in the distributed environment. And the challenge is whether they've restricted themselves to a particular access mechanism, you have to come in through the web, whether they've restricted themselves to a particular type of storage, I can manage all this data as long as it's on file systems, whether they've restricted themselves to a particular preferred access mechanism, etc. And so if a system meets your requirements, maps to the type of resources you're doing, and it's a simpler environment, you should always use it.
To revert to the earlier question of commodity disks, my understanding is, I don't know what Google's failure rate is, but you mentioned a different kind of failure rate, not the catastrophic failure of individual disks, but I think you were saying simply an identifiable bit failure.
Yes.
And how does that match catastrophic collapse of disks?
We normally see catastrophic failures either very early in the lifetime. So if it survives the first month and after that we're pretty much okay, or it's at the end of life.
Well, naturally.
After 5 years.
That's when you die.
Yes, but it won't be until the warranty has expired. And then in between, it's bit flips. So we have been keeping statistics on our commodity disk. We have 30 terabytes of commodity disk in-house. The person who was maintaining the system, every time a disk was reported as failing, would take it offline, run all sorts of diagnostic tests on it, try to figure out why it had failed. And for the vast majority of the disk, he could not find a cause, and he put it back into production. And then he would track whether the disk, after he put it back into production, saw any errors, and typically they wouldn't. So many of the challenges are that it wasn't necessarily the disk itself. It could have been the cabling. It could have been crosstalk in the cable. It could have been a loose cable. It could have been who knows what. could have been a cosmic ray coming through and flipping it for us, and the disk was fine until the cosmic ray interfered. And therefore, there's a rate at which you will see errors, no matter how good the disk is. And therefore, you really just have to keep checking and monitoring. Yes?
This overall enterprise is quite expensive and complex. You have big machines, big disks, a lot of people involved in it. Now, sort of from my perspective, one of the interesting things that are sort of coming out of the science grid computing program are several trends, but one is the move towards utility computing. The manufacturers may, instead of selling as machines, may sell it as services, compute services, storage services, whatever.
Mm-hmm.
The other is this sort of identification that the interface between those facilities and the users may be some service space, which will do things for you. Could you see some refactoring of this activity to fit into that, where sort of you don't, own the big machines on them, but you sort of run an archive.com service and utilize that, but all that
Yes.
complexity is sort of backed into some utility operation?
So there are multiple answers. One is that it takes 18 minutes to install that entire environment plus a Postgres database on a Mac. So you could be running it today with no problem and have your own personal data grid. The second comment is a service-oriented architecture is a good one, and archives preservation environments are quite interested in that, where the service is not only maybe the storage of the data, but it's also these transformative migrations of the encoding format. It might be validation that the data is uncorrupted, or a variety of possible operations. So we have had groups that would like to see a service that they could then use where somebody else incurs all the risk that there might be a problem and has written a service level agreement making some statement about what they do if a problem does occur, that there are multiple copies or geographically separated or whatever. So we expect in the future that the specification of these service level agreements becomes critical, and how you enforce them. What happens if the service level agreement isn't met? Do they just say, well, we tried our best? Or can you state that behind the service level agreement there were a set of mechanisms that will help guarantee that data hasn't been lost, i.e. the correct number of copies geographically distributed? Yes?
Well, I'm going to ask a question about the social communities around these grids. And in many of you, throughout your talk and in many of your answers, you've spoken about communities, you've spoken about collaborations, you've spoken about agreements, and what I'm just wondering is, are there any one of these projects that you've listed here, is there anywhere where you've noticed just breakdown? The thing doesn't work, and it doesn't work not because of technical reasons, but it doesn't work because of social reasons, such as an inability to share, or an inability to trust, or not seeing eye to eye as to what
Yes.
this data is for, or inappropriate usage.
I can quote Mark Ellisman, who runs the Biomedical Informatics Research Network for the National Institute of Health. This is a collaboration between 17 to 25 research hospitals and academic institutions who are working on neuroscience. So they all have images of the brain in some modality, and they're investigating either Alzheimer's or other diseases. And the challenge that NIH faced was that each researcher at each institution was working completely independently of the rest of the community. And NIH wanted all of the researchers to start sharing data, start sharing ideas so they could make progress faster. In order to help provide an incentive, they actually analyzed all the audit trails that we maintain so they could track how much data was accessed at a given institution by other institutions, and how much, so it's both ways, how much data you access from other institutions, how much data someone else accessed from your institution. And that was then used as the figure of merit within the overall project to show that the collaboration was working. It wasn't whether or not you had assembled a large collection, it was how much data you were sharing. So this was an incentive from the funding agency, and the implication was that unless you agreed to play, you wouldn't be funded. When you talk to the individual researchers, they stated that being able to access somebody else's data is nice, it's wonderful, it helps progress. But the purpose of our research is to develop unique understanding that nobody else has, and then promote that to the point where everybody else accepts that our view of the universe is correct. And so they have just the opposite tendency to say, our goal is to show that we have the correct understanding of the scientific issues that are going on. Some communities think they can do that better if they hold that scientific understanding within the group. There are other communities, an example is Mike Norman, who does astrophysics, early structure of the universe, wants to publish his simulation results as soon as he creates them, even before he's looked at them. And his position is that if somebody else looks at my output and finds a problem, hooray, they found something that I don't have to search for and discover. And
Publish before you see it yourself.
Yes. So he wants to publish immediately and promote and therefore draw more people into his activity because they're looking at his results. So in effect, he's taking his small local project and trying to extend it to the entire world. So it's entirely in your cultural mindset whether you're more comfortable keeping it local till you're certain that nobody's going to object, find the fatal flaw in what you're doing, or whether you want to provide all the information as soon as possible so somebody finds the fatal flaw before you put a lot of effort into it.
Just one other question. Why are the funders giving incentive for collaborations? What are they seeing collaboration?
In all the projects that collaborate, progress is made faster. There's more expertise involved in understanding the physics. There's a better access to possibly contradictory information that's coming from another site, and you get that sooner so you can decide whether or not you have to revise your view of the universe. And therefore, collaboration helps you both analyze, get access to more material, and it helps you validate, get assurances that yes, you're on the right track quicker. And that way you don't spend as much time going down the wrong path.
This is the same thing they say in the Linux and open source community. Many eyeballs speed debugging.
Yes.
Do any collaborations cross over from the academic into the public sector? Is some of this data publicly available?
All of the collaborations we work with have public data. Some of them, it again depends upon the community. Some of them like to keep the data within the community for a year or a year and a half, and then it becomes public, anybody can access it. Typically they do it because they say they want to remove artifacts so that they won't put out bad data, which is quite reasonable. I'd rather see good data than bad data. Other people want to do it so they can mine the information and get the Nobel Prize before somebody else does.
Are there any data type constraints on this system?
The version we have allows you to manage any type of data. No constraints on what the data type is.
The thing that also strikes me as interesting, though, is that although it may be more efficient, it still requires active management on a regular basis of the assets.
Yes. If technology were fixed, you could reduce some of the management requirements. If when I stored data, it never became corrupted, I could reduce management requirements. If the community did not evolve its understanding of the collection, add new attributes over time, I could reduce the management environment. But everything is changing, and therefore you have to continue to respond to the changes.
Could you go back to your image of the three interlinks?
At the end. There we go.
How do they establish trust?
What we have to do is register the existence of this data grid with respect to that one. So there is a set of administrator commands where the administrator of each data grid has to talk and establish either a shared secret or a GSI certificate that they can use to authenticate between themselves. When that is done, then this grid sends to the other grid the set of information about the metadata catalog where this is storing all its metadata, and this provides the correct control permissions. When a user in this grid accesses data in the other grid, this grid says, I know that this person came from zone 2. So I will send the request back to zone 2, and zone 2 will have to authenticate that this really is the person they claim to be. And then the zone 2 will send a notification back to zone 1 saying, yes, the person authenticated themselves correctly, they really are who they say they are, and then zone 1 can apply their access controls on that person.
So why did you decide 3, why did you decide 3 was the optimal trust
Because that's
relationship?
the minimum number I can use
Can't
to
afford
implement a
more.
deep archive.
Can't afford more.
But I could do 4 or 5 or 6 or 10 or whatever.
But 3 is the minimum number.
Yeah. So if I try to turn this into the deep archive, then some information from this grid is known in the external world. They know the name of the person, they know a location. It's not really hidden.
One last question. One of the extremely exciting things about this work is that it really does begin to break down barriers between the arts, humanities, sciences, cultural heritage. And one of the obstacles we're facing is the kind of work that's being done in grid technology in the sciences is not open source. And so, but yet in the, say, cultural heritage or humanities community, there's a kind of assumption that things are open source.
You mean open source or open content?
Open source and Berlin Declaration, so open source is
So open source the content, are we talking software as well?
everything is open source. And so I wonder if you have some ideas about how to square this circle about open sources versus non-open source, since most of the funding agencies in the United Kingdom are now requiring that you have open source policies, even for grid. So EPSRC is even demanding that you have open source grids.
Yes.
So I wonder if
So
you
I've learned in Australia that my software is open source because open source does not mean no cost. It means anybody can gain access to the source. So in this case, for the storage resource broker software, we distribute the source to any academic institution. We're allowed to do that. However, UCSD sold the commercial rights for the software to a company to market to commercial companies. And the agreement that we're negotiating with them is that an commercial company can get a copy of this academic source if they assign the correct agreement with Nirvana Storage. So that way anybody can gain access to the source. Our second effort along this line is that we really want to have a BSD license version for open source for software that then is accessible by anybody under any requirements. To do that, we have to develop a new version of the software in collaboration with the international community, so we're starting that effort.
And who's part of that effort?
We have talked to groups in the UK, Kirsten Cleese, the UK eScience Data Grid. We've talked to groups in Taiwan, so the Academia Sinica. We've talked to groups in Australia, the Australian National University, the APAC program, etc. And we're finding communities that believe that creating a rule-based data management system is the correct next step, next set of technology that should be developed. And that would then be an open source software.
I have 2 other quick questions.
Okay.
One about what metadata models do you recommend? Or will it work with premise or ISO 23801 or?
We find that each community we work with chooses a different metadata model. So in the work with the UCSD libraries, they use a METS profile, and it's an official METS standard, and they've migrated or mapped all of the descriptive metadata they use within their community to that profile. We work with communities that are happy with, so NSDL is happy with the education extensions to Dublin Core as their metadata set. So we support that. We work with communities that require hierarchical metadata like the National Archives, the Life Cycle Data Requirements Guide. So there are all sorts of, quote, standards that the community we work with insists on using. And we don't decide which one is better. Our goal is to allow you to pick the one that meets your requirements and then be able to implement it within this environment.
And archival preservation is a very long-term thing, 100 years. What is it about this particular approach that makes it?
Did you say 100 years?
Oh, hundreds of years, thousands of years. I mean, but let's not try and let's just give him 100 years to think about to be fair to the poor guy. What is it about the pathway, the development of this technology that makes it particularly conducive to long-term thinking?
When we worked with the National Archives, they had an electronic access project which had assembled a terabyte of data, 250,000 images. And they had picked a set of technology at the time they implemented that project. And they discovered that one of the vendors of a component of the technology had gone out of business. It was no longer available. And that if they wanted to migrate the technology to a new, more current operating system, they would not be able to do it because the person who developed part of the technology was no longer there. So they wanted an environment where they could demonstrably migrate from one vendor's solution to the next vendor's solution without having any real hurdles to encounter in the way. They wanted the ability to add new access mechanisms because new ones keep coming up, new interaction protocols, new metadata standards. They needed the extensible schema. They needed to be able to use a variety of databases, a variety of storage systems. And they saw this technology as actually allowing them to do it. So we called it infrastructure independence.
So ruling out vendor unique solutions rules out innovations which are owned by one vendor.
We can talk to any vendor's product. And if they have a unique product, we will talk to them.
I see.
But at the same time, you work with OCLC and think institutions which aren't going to go out of business because they're not there to
Yes.
do commercial ventures.
So what we discover is that each community really wants to put their preferred access mechanism on top of this. They want their preferred set of metadata. They want their preferred schema. And so you need an infrastructure that allows them to make that choice without any constraints. The other part of this is I have talked to other archives in which they had built an environment and the vendor had gone out of business and they had to recover the preserved records, but that in the process of storing the preserved records, the vendor would have encoded it with their proprietary format. And the cost of reverse engineering the proprietary format would end up being onerous, such that they just had to abandon the collection. They could not afford to recover it. So this environment doesn't do that. The data is stored as files on file systems. I can go into the file system, read all the data.
I have to tell an anecdote. I know a woman who lived with a guy who built her a database for her business. He then left her on an unfriendly basis and didn't leave the source code.
Yes.
So it happens at all levels.
Yes.
Reagan, thank you very much.
Thank you.